Hello folks, how's everybody doing out there? In this episode of the history of software in three-letter acronyms, K is for KiB, KiB? Hands up who's thinking, what's a KiB? And I'm not even sure if that's how you'd pronounce it. I've never heard anybody say it out loud, so I honestly don't know if it's an acronym or an initialism. The important bit is the letter K, which in computer acronyms, and in science and technology generally, usually refers to kilo. Okay, it could be referring to kelvins, the SI unit of temperature, and yes, 1000 kelvins is called a kilokelvin, kk, but we're not here to talk about temperature, we're here to talk about memory, specifically kilobytes of system memory. Because for a while back there, K wasn't a three-letter or even a two-letter acronym, it was just K. The ZX Spectrum 16K, the BBC Micro 32K, the Spectrum 48K, then the Commodore 64 started a trend of not including the K at all, which means it might be a strong contender for the first zero-letter acronym. Then Amstrad followed up with the 464 with 64K of RAM, the 6128 with 128K, and then two PC clones called the 1512, 512K of RAM, and the 1640. And veterans of MS-DOS will be looking at that number, 640, and maybe experiencing just a touch of discomfort. Because for more than a decade, the PC had a hard memory limit of 640 kilobytes. And that limit was a massive pain in the ass on an almost daily basis for an entire generation of PC users. The reason for that limit goes all the way back to the design of the original IBM PC, also known as the 5150, which is also the name of one of the best rock albums of all time, 5150 being the first album Van Halen recorded with Sammy Hagar back in 1986. That album was named after Edward Van Halen's home studio where it was recorded, and the studio was apparently named after the section of the California Welfare and Institution Code that covers authorized personnel placing somebody in temporary custody for psychiatric health reasons. Now, I'm not saying that the IBM PC's memory management was so dangerously unhinged that it should have been locked up for public safety. I'm just saying those numbers are kind of a weird coincidence. But why the limitation? Okay. Imagine you are filling out your address on a form and you've got to write down your house number, and they've only given you 2 boxes to put it in. Every house from 1 Acacia Avenue to 99 Acacia Avenue is fine, but 100 Acacia Avenue won't fit. It doesn't matter whether the house actually exists or not, we can't send mail there because there isn't enough address space to talk to it. If we add a 3rd box to the form, well, now we can handle every address up to 999 Acacia Avenue. In computer memory, the digits aren't decimal, they're binary. They're bits, 1 and 0. Each extra bit gives us twice as much address space. And the houses aren't houses, they're memory locations, which by this point in history are standardized as 8-bit bytes, thanks to Fred Brooks' work on the IBM System 360, which I talked about in an earlier episode. So the limiting factor becomes address space. How many different memory addresses can the CPU handle? The IBM 5150, more commonly known as the PC XT, used the Intel 8088 processor, which had a 20-bit physical address bus. This meant it could address 1,048,576 unique memory addresses, and with 1 byte at each address, that is 1 megabyte of address space. But that had to include every single storage location that the CPU might need to read or write, the system ROM, the BIOS, and the memory-mapped display buffer for the video adapter. So the designers of the PC XT and the MS-DOS operating system that shipped with it, and yes, I know that the version that actually shipped with the IBM PC was called PC-DOS, had to make a call. How much of that megabyte of address space should we reserve for the system, and how much should be available to applications? They figured 384 kilobytes should be enough for BIOS and memory-mapped I/O, and that left 640 kilobytes for everything else. No big deal. By the standards of the time, that was an unimaginable amount of memory. Almost all previous systems used an 8-bit address bus that limited them to 64 kilobytes of RAM. Bill Gates has been widely quoted as having said 640K ought to be enough for anybody, but he never actually said anything like that. As he wrote in 1996, "I've said some stupid things and I've said some wrong things, but not that. No one involved in computers would ever say that a certain amount of memory is enough for all time." Problem was, the PC was wildly successful. The 8088 became the 8086, and then the 286, the 386, 486, the Pentium. But as long as customers needed reverse compatibility for their old MS-DOS applications and games, that 640K limit was a fact of life. Sure, there were ways to work around it, as long as you understood the difference between high memory, extended memory, and expanded memory, and had enough basic memory available to load the driver files for whichever memory model worked best with the game or application you were running today. If you're one of those gamers of a certain generation who ever had to get Wing Commander 2 to run on a 386 PC with MS-DOS, you'll probably remember creating boot disks that would load DOS with just enough drivers that your mouse and sound card would work, but you'd still have enough basic memory left to load the game. Finally, in the mid-1990s, Windows NT comes along, a properly 32-bit operating system that could address up to 4 gigabytes of memory in one glorious continuous block. And if you really needed to run your old MS-DOS programs, it would run them in something called a virtual DOS machine, which sort of mostly worked some of the time as long as you weren't trying to run Wing Commander 2, which is why a lot of us old-timers kept Windows 95 or 98 installed alongside it in case we wanted to fire up any of our old games for a bit of a nostalgia blast. Or we installed Linux and found out that trying to get games to run on Red Hat 4 was often a lot more fun than actually playing them. And today, well, I'm editing this video on a 64-bit AMD Ryzen with 128 gigs of RAM, which still isn't really enough. A terabyte would be nice, but really, I'm thinking a petabyte ought to be enough for anybody. Which brings us rather nicely to the second part of this video. I started off talking about how K has long stood for kilobyte, and we've gone from kilobytes to megabytes to gigabytes to terabytes to petabytes and exabytes, and I'm sure eventually to zettabytes and yottabytes and ronabytes and kuetabytes. But it turns out we've been talking about K and megs and gigs for the last few decades without really being entirely sure what we actually mean. See, kilo goes way back. It derives from the ancient Greek word helioi, meaning 1,000, and it's been used as a prefix denoting 1,000 of something since 1795, the year that the French Academy of Sciences introduced the first metric system of measurement, which defined the kilogram as the mass of a litre of water. And for humans, with our 10 fingers and our base 10 counting system, 1,000 is a nice round number. But for a binary computer, 1,000 isn't a round number at all. No, 1,024, that's a nice round number because that's 2 to the 10th power. So we ended up with this slightly odd convention where a kilogram was 1,000 grams, but a kilobyte was 1,024 bytes. Which wasn't really a big deal. 24 bytes doesn't make a huge amount of difference, and if anybody was going to quibble it, they'd realize the error is in their favor. Hey, you got 24 bytes of extra memory for free. Which is all well and good until marketing gets involved. You see, big hard drives, drives with a lot of storage capacity, are more expensive than small hard drives, because when you punch through all the abstraction layers of files and folders and bytes, every bit of storage on a mechanical hard drive is actually a uniquely addressable microscopic magnetic particle sitting on the surface of a steel disk that's spinning at a few thousand revolutions per minute. You want to build a 10 megabyte hard drive? You've got to get about 86 billion of those particles onto the disk platters in exactly the right places and figure out how to read and write each one as it goes whizzing under the drive head at 100 kilometers per hour. And because the physical unit is a standard size, if you want to build a 20 megabyte hard drive, you've got to fit 172 billion particles into the same amount of space. Then at some point in the mid-1980s, some bright spark working in the marketing department of one of the hard drive manufacturers goes, "Hang on lads, I've got an idea. Instead of figuring out how to fit all 20,971,520 bytes onto a disk, why don't we just fit a nice round 20 million on there? That'll make the drives cheaper to manufacture, and the best part is we can still write 20 megabytes on the box in big letters." And so they did. And for a while, nobody really noticed. But as hard drives got bigger, folks started getting wise to the difference. Mainly because they'd buy a PC with a 1 gigabyte hard drive, fire up Windows 98 SE, open the drive properties and go, "What? 950 megabytes? But I paid for a gigabyte." Sure, there are 1 billion bytes on that disk, and if you divided that by 1,000,000, you'd get 1,000. That's the gigabyte you paid for. But Windows isn't dividing by 1,000,000. To Windows, a megabyte isn't 1,000,000 bytes. It's 1,048,576 bytes. And your shiny new gigabyte hard drive only has room for 950 of those. And if you actually measured the drive space in binary gigabytes, it gets even worse, because 1 billion bytes, a decimal billion, is only 0.93 binary gigabytes. And to make things even more entertaining, the bigger the drive, the bigger the difference. A decimal kilobyte versus a binary kilobyte, you lose 24 bytes out of 1,000. 2.3%. A decimal megabyte is 95% of a binary megabyte, so you lose about 4.5%. A gigabyte, you lose 7%. A terabyte, you lose 9%. And 9% of a terabyte is, well, it's 99 gigabytes if you're a computer scientist and 92 gigabytes if you work in Western Digital's marketing department, but either way, it's quite a lot of space. You could almost fit an entire installation of Baldur's Gate 3 in that. The problem is, the hard drive manufacturers weren't actually in the wrong here. I'm not defending their motives, but when it came to the crunch, in the blue corner, there's the hard drive manufacturers, mathematicians, physicists, chemists, engineers, and basically the entire metric system. And in the red corner are some computer nerds shouting about Microsoft Windows. Incidentally, while we're on the subject of memory and of marketing departments messing with the numbers to make things sound impressive, let's take a moment to talk about DDR memory. DDR stands for double data rate. You see, hooked up to the RAM in your PC or your phone or whatever kind of device, because even your lawnmower probably has a RAM chip in it somewhere, there is a clock signal, tick-tock, tick-tock, keeping everything nicely synchronized and making sure when you read or write a load of data, it all gets read or written at the same time. The first generation of PCs used something called fast page memory, FPM, but they didn't have to call it that because there wasn't any other kind of memory, so it was just called memory. Then, around the time that Windows 95 came out, we started seeing something called EDO-RAM, extended data out, which was just a little bit faster than fast page memory because it kept data in buffers so that when the system went to read the contents of the memory, it wouldn't have to wait for it to be ready. A bit like the way McDonald's always has a few cheeseburgers already cooked and ready to go, so when you order one, you don't have to wait for them to cook it, a technique known in memory engineering as eliminating wait states. EDO-RAM speed was expressed in nanoseconds. How long does it take between the CPU going, hey, get me that data, and the CPU actually receiving that data? 120 nanoseconds, then 100, then 60, then around the time that EDO-RAM started being replaced by synchronous dynamic RAM, SD-RAM, somebody in the marketing department went, hey, this is no good. The RAM is getting faster, but the numbers are getting smaller. Can we make the numbers get bigger again? And so instead of measuring memory speed in cycle time, we switched to measuring it as a frequency. Instead of 15 nanosecond RAM, we got 66 megahertz SD-RAM, then 100 megahertz, 200 megahertz, 400 megahertz, and the marketing people were happy because the numbers are going up again, which means the memory clock, tick-tock, tick-tock, is getting faster. And then DDR memory is invented. It runs at the same frequency, but now you get 2 read-write operations per clock cycle. Or to put it another way, up until now, the CPU could only read and write memory on the tick. With DDR, it can read and write on the tick and on the tock, which effectively doubles the data rate of the memory, hence the name. Which is all brilliant, except the marketing people go, woohoo, we like big numbers, and so they invent another new unit, MTS, megatransfers per second. How many million separate read-write operations can that memory bank do in 1 second? Cool. So if you've got a DDR RAM chip that's clocked at 1800 megahertz, it'll do 3600 megatransfers per second. So far, so good. Except the marketing people don't stop there. Somebody somewhere decides that it would be a good idea to mix up the units. After all, 1 hertz is defined as 1 cycle per second. So if a RAM chip can do 3600 million read-write cycles per second, that's basically the same as 3600 megahertz, right? And just to make things extra spicy, modern DDR memory goes so unbelievably fast that it's common for manufacturers to advertise something called SPD speed and something called tested speed. Tested speed is the upper limit. Any faster than this, and you are pretty much guaranteed to have problems. SPD speed is the lower limit, the speed at which the memory is basically guaranteed to work except when it doesn't. The machine that I'm using to edit this video has 4 32GB sticks of Corsair DDR5 6000 MTS memory. That's memory advertised by the manufacturer as having a tested speed of 6000 megatransfers per second, has a sticker on the box saying it'll run at 6000 megahertz, an SPD speed of 4800 megahertz, and which is actually only running at 3600 megahertz right now, because as I found out after I put it all together, you can't run 4 sticks of DDR5 memory at full speed because it'll rip a hole in the space-time continuum or something. Or at least I can't. If you can, by all means drop me a comment telling me how you did it. So in the system BIOS, it's set to run at 3600 megahertz. Windows Task Manager says it's running at 3600 megatransfers. And CPU-Z, or is it CPU-Z? A wonderful little program that'll tell you all sorts of useful statistics about your hardware. It says that it's running at 1796 megahertz. I'm hoping it'll all get sorted out in a future BIOS update or something, but until then, 128 gigs of RAM running at 3600 megatransfers per second is still a ridiculous amount of memory bandwidth, so I'm not losing any sleep over it. Anyway, back to our disk space problem. There were a handful of class action lawsuits in the 2000s, with customers arguing that manufacturers had misled them about the capacity of their hard drives. These were mostly settled out of court, with better product labeling being a condition of the settlement, and these days, if you look closely at the product descriptions and packaging of hard drives, you'll probably see a little disclaimer somewhere telling you that a gigabyte is 1 billion bytes. Here's the product listing for an 8 terabyte Samsung NVMe drive, and here's the small print telling you that that actually means 8,000 gigabytes, and that gigabyte is 1 billion bytes by capacity as defined by IDEMA. That's the International Disk Drive Equipment and Materials Association, who are apparently the people in charge of this kind of thing. But there might be another reason you don't hear folks complaining about this anymore. In 1998, the International Electrotechnical Commission, another group I'd never heard of until I was making this video, created a new set of prefixes. Kilo always means a decimal thousand, and if you wanted to refer to 1024 bytes, you wouldn't say kilobyte, you'd say KiB byte, a contraction of kilo binary. 1024 KiB bytes makes a mebibyte. 1024 mebibytes makes a GB byte, and so on. Tebi bytes and Pebi bytes and XB bytes and Zebi bytes and Yobi bytes. Now, I was studying undergraduate computer science at the time, and I think I remember one of our lecturers mentioning these units in passing. I can't be certain, but if they did, that would have been the only time in my life I have ever heard anybody use any of these terms out loud. In 25 years of software development, network support, meetups, conferences, and watching YouTube videos, I do not think I have ever heard anybody refer to a GB byte of memory. And personally, I think that's because KiB byte and mebibyte and GB byte are up there alongside Spongel and Snollygoster as words that are hard to take seriously because there's just something inherently funny about the way they sound. And perhaps that is the real beauty of their solution. When no alternative existed, it was easy for people to get up in arms about having to deal with 2 different kinds of gigabyte. But now, given the choice between using the word gigabyte in technical conversation, or just shutting up and accepting that really we all knew what kind of gigabyte they were talking about in the first place, the controversy seems to have quietly gone away. Finally, you'll notice that throughout this video, I've been pronouncing gig with a hard G, which is kind of weird, because like a lot of people, the first time I ever encountered that prefix was the movie Back to the Future, and Doc Brown bouncing around his workshop shouting 1.21 gigawatts! According to Collins Dictionary, both giga and jigger are acceptable pronunciations, but at some point along the way, it seems that British English decided that giga was the way to go. And in the course of putting all this together, I dug up another one of those lovely little quirks. In the movie, Marty McFly travels back in time to 1955, and he and Doc spend the rest of the movie figuring out how to harness a bolt of lightning to produce the 1.21 gigawatts of power needed to send him back to the future. When past Doc sees future Doc on a VHS tape talking about 1.21 gigawatts, he knows exactly what it means, but Jigger wasn't adopted as an SI unit prefix until 1960. Well, not officially. The Oxford English Dictionary reports that the earliest written use of the prefix was in the Proceedings of the International Union of Pure and Applied Chemistry in 1947. So maybe Dr. Emmett Brown was just an extremely well-read scientist. Or maybe there was a bit of extracurricular time traveling going on behind the scenes. Which would also explain how Marty McFly invented rock and roll in 1955, playing a Gibson ES-345 guitar that wasn't introduced until 1958. And Marty's onstage guitar pyrotechnics, you know, the stuff you guys aren't ready for yet, but your kids are gonna love it. Inspired by the man behind the other 5150, the late, great Edward Van Halen, which I realize has nothing to do with kilobytes, but it's a nice note to end on. Folks, I hope you found that interesting. In the next installment of this series, L is for LLMs. Yep, it's time to talk about large language models, embeddings, vector databases, the history of AI, and why a lot of very smart people have been confidently saying since the 1950s that we're only 5 years away from a computer being smarter than a human, despite this turning out over and over again to not, in fact, be true. Until then, you all take it easy out there, look after each other, and I'll catch you all next time. Bye-bye.